more than 3 decades, the B-2 Spirit represented the pinnacle of stealth bomber design. And when it first entered service, it redefined how engineers thought about survivability, range, and precision in long-range aviation. Its flying wing shape, advanced materials, and low radar visibility were revolutionary for their time, setting a standard that few aircraft in history could match.
And when I think about the mission statement of the United States Air Force, the fly, fight, win, air power, anytime, anywhere, that's what the B-21's about.
However, aerospace technology does not stand still. Over the last 30 years, advances in computing power, materials science, digital engineering, and systems integration have completely reshaped how modern aircraft are designed. The B-21 Raider is not simply a newer version of the B-2. It is the result of an entirely different design philosophy built around adaptability, efficiency, and long-term relevance. Rather than focusing on a single mission profile or threat environment, the B-21 was engineered to operate in a far more complex and interconnected world. Every aspect of the aircraft reflects lessons learned from decades of operational experience, combined with modern tools that were not available when the B-2 was conceived. This comparison is not about replacing a legendary aircraft or diminishing its legacy. Instead, it highlights how a new generation of engineering approaches has transformed what a stealth bomber can be. The B-21 Raider represents a generational shift, one that emphasizes flexibility, sustainability, and system-level design over traditional benchmarks of size or payload alone.
The B-21 looks very similar to the B-2 because the fundamentals of stealth and long-range penetrating air are built around the concept of a flying wing, and that.
When the B-2 Spirit was designed in the late Cold War era, aerospace engineering relied heavily on physical prototypes, wind tunnel testing, and limited computer modeling. Engineers worked within the constraints of the technology available at the time, optimizing the aircraft for a specific strategic environment. The primary goal was straightforward: create a bomber that could evade radar while delivering long-range capability. The result was groundbreaking, but it was also shaped by the limitations of 1980s design tools. The B-21 Raider reflects a completely different design philosophy. Instead of focusing on a single threat or mission, it was built around adaptability from the very beginning. Advanced digital engineering tools allowed designers to simulate millions of scenarios before the aircraft was ever physically assembled. Every surface, angle, and internal layout was optimized using high-performance computing, allowing engineers to refine the design with a level of precision that was impossible decades ago. Another major difference lies in system integration. The B-2 was designed as a standalone platform with upgrades added gradually over time. In contrast, the B-21 was conceived as part of a broader network of systems. Its architecture allows new technologies to be integrated with minimal structural changes, ensuring the aircraft remains relevant for decades. This shift in philosophy marks a move away from rigid, purpose-built designs toward flexible platforms that can evolve. The B-21 Raider embodies a modern approach to aerospace engineering, one that prioritizes long-term adaptability over fixed performance benchmarks. Stealth technology has always been the defining feature of advanced bomber design, and the B-2 Spirit was a milestone in this field. At the time of its development, stealth focused primarily on reducing radar detection from forward-facing angles. This approach was highly effective against the radar systems of its era, which were often limited in coverage and processing capability. For decades, this design philosophy provided a significant technological advantage. Modern detection environments, however, are far more complex. Contemporary radar networks use multiple sensors, varied frequencies, and data-sharing systems that monitor airspace from nearly every direction. In this environment, stealth can no longer rely on directional optimization alone. The B-21 Raider was designed with this reality in mind. Rather than minimizing detection from specific angles, the B-21 emphasizes what engineers describe as all-aspect or 360-degree stealth. Its shape, surface alignment, and internal structures are engineered to manage electromagnetic energy regardless of the direction from which it is encountered. This holistic approach significantly reduces the aircraft's overall detectability across a wide range of sensing methods. Equally important are advancements in materials. The B-21 incorporates newer composite structures and embedded stealth treatments that are more durable and efficient than earlier generations. These materials contribute to consistent performance while reducing the maintenance demands traditionally associated with stealth aircraft. Together, these changes represent an evolution rather than a simple refinement. The B-21's stealth philosophy reflects a modern systems-level approach designed for long-term effectiveness in an increasingly sophisticated detection landscape. At first glance, the B-2 Spirit's large flying wing design appears to offer clear advantages. Its wide wingspan allows for significant internal volume, enabling high payload capacity and extended range. When it was introduced, this size made sense as mission requirements emphasized carrying large quantities of weapons over intercontinental distances. The B-21 Raider takes a noticeably different approach. It is more compact, with a reduced wingspan and overall footprint. This change is not a compromise, but a calculated engineering decision. In stealth design, size directly influences detectability. Every additional surface area increases the likelihood of interacting with radar and other sensing systems. By reducing overall dimensions, engineers were able to significantly lower the aircraft's observable signature. Smaller size also brings important efficiency benefits. A more compact airframe requires less structural material, reducing weight and improving fuel efficiency. This contributes to lower operating costs and simplifies logistics over the aircraft's service life. Additionally, the B-21 size allows it to operate from a wider range of airfields, increasing deployment flexibility without relying on highly specialized infrastructure. Payload capacity is another area where efficiency outweighs raw numbers. While the B-21 carries less total weight than the B-2, advances in precision-guided systems mean fewer munitions are needed to achieve the same operational effect. This shift reflects a broader trend in aerospace design, prioritizing efficiency, adaptability, and sustainability over maximum size or load. One of the most significant differences between the B-2 Spirit and the B-21 Raider lies beneath the surface, quite literally, in the materials used and how those materials are maintained. When the B-2 was developed, radar-absorbing materials were revolutionary but also highly demanding. These coatings required precise environmental conditions, frequent inspections, and specialized facilities to preserve their effectiveness. While highly capable, this approach resulted in complex maintenance cycles and limited operational flexibility. The B-21 Raider reflects decades of progress in materials science. Rather than relying heavily on external coatings alone, the aircraft integrates stealth characteristics directly into its structural materials. Advanced composites and embedded treatments reduce reliance on fragile surface layers, making stealth performance more consistent over time. This design approach significantly improves durability while maintaining low observability. Maintenance philosophy has also evolved. The B-21 was engineered with sustainment in mind from the earliest design stages. Components are easier to access, replace, and inspect, reducing downtime between missions. Digital diagnostics allow maintenance crews to monitor aircraft health more efficiently, identifying potential issues before they become major problems. This shift has important long-term implications. Lower maintenance demands translate directly into higher availability rates and reduced operating costs. It also allows the aircraft to operate from a broader range of facilities, rather than being tied to highly specialized support infrastructure. Together, these material and maintenance innovations represent a fundamental change in how advanced aircraft are sustained, ensuring the B-21 remains effective and economical throughout its service life. Cost and production efficiency are often overlooked when discussing advanced aerospace systems, yet they play a decisive role in long-term capability. The B-2 Spirit was an extraordinary technological achievement, but its development occurred in an era when digital production tools were limited. As requirements evolved and production numbers were reduced, development costs were spread across a very small fleet, dramatically increasing the cost per aircraft. The B-21 Raider was designed with these lessons in mind. From the outset, affordability and scalability were treated as core design requirements rather than secondary considerations. Advanced digital engineering, modern manufacturing techniques, and tighter integration between design and production have significantly reduced inefficiencies. This has enabled a far more predictable development process with fewer late-stage modifications. Production scalability is another major advantage. The B-21 program is structured around a larger planned fleet size, allowing fixed development costs to be distributed more effectively. This approach reduces unit costs while supporting steady production rates over time. Modern tooling and automated processes further improve consistency, quality control, and delivery timelines. Sustainment costs are also lower by design. Simplified maintenance, modular systems, and improved material durability reduce life cycle expenses, making the aircraft more economical to operate over decades of service. Together, these factors create a system that is not only advanced, but also financially sustainable. The B-21 demonstrates how modern aerospace programs can balance cutting-edge capability with responsible production and long-term affordability. Operational flexibility has become a defining requirement for modern aerospace platforms, and this is an area where the B-21 Raider reflects a clear generational shift. The B-2 Spirit was designed around a specific strategic concept, with capabilities tailored to a narrower set of mission profiles. While it has proven adaptable over time, integrating new systems has often required extensive upgrades and structural modifications. The B-21 approaches flexibility as a foundational principle rather than an afterthought. Its internal architecture is built around modular, open system design, allowing new sensors, software, and mission systems to be integrated with minimal disruption. This enables the aircraft to evolve as technology advances without requiring costly redesigns. System integration extends beyond the aircraft itself. The B-21 is designed to operate as part of a broader digital ecosystem, seamlessly exchanging data with other platforms and support systems. Advanced onboard processing allows it to manage information efficiently, supporting coordination, situational awareness, and mission-level decision-making within a connected operational framework. Another key aspect is adaptability and deployment. The B-21's design allows it to operate from a wider range of locations with fewer infrastructure constraints. This enhances responsiveness while reducing reliance on highly specialized facilities. Taken together, these elements create a platform that is not locked into a single role or configuration. Instead, the B-21 functions as a flexible system designed to integrate, adapt, and remain relevant across decades of evolving technological requirements. Designing an advanced aerospace platform is no longer just about meeting today's requirements. It is about ensuring relevance decades into the future. The B-2 Spirit was a product of its time, built around fixed systems and mission concepts that reflected the strategic environment of the late 20th century. While it has remained effective through upgrades, those enhancements were often complex and resource-intensive. The B-21 Raider was engineered with longevity as a primary objective. Its digital design framework allows for continuous modernization without fundamental changes to the airframe. Software-driven systems enable rapid capability updates, reducing reliance on major hardware overhauls. This approach ensures the aircraft can adapt as new technologies emerge. Future-proofing also extends to integration readiness. The B-21 is designed to accommodate advancements in sensing, data processing, and automation as they mature. Its internal systems can support higher computational demands without compromising performance, allowing it to absorb next-generation technologies over time. Another critical factor is sustainment over a long service life. By prioritizing durability, maintainability, and modularity, the B-21 minimizes the risk of becoming obsolete due to logistical or operational constraints. This ensures consistent availability and effectiveness well into the future. Ultimately, the B-21 represents a shift from static capability toward continuous evolution. Rather than being defined by a single technological moment, it is structured to grow alongside the aerospace and digital ecosystems that will shape future aviation. The comparison between the B-21 Raider and the B-2 Spirit is not a question of which aircraft is better, but of how aerospace design itself has evolved. The B-2 was a landmark achievement that reshaped expectations of stealth, range, and precision. It set standards that influenced generations of aircraft design and demonstrated what was possible with the tools of its era. The B-21 Raider builds on that legacy by embracing a fundamentally different approach. Rather than maximizing size, payload, or singular performance metrics, it prioritizes adaptability, efficiency, and long-term sustainability. Every design choice reflects lessons learned from decades of operational experience, combined with modern digital engineering methods that allow continuous refinement and evolution. What defines the B-21 is not just its technology, but its philosophy. It is a system designed to integrate, upgrade, and remain relevant in an environment where change is constant. Its reduced maintenance demands, scalable production model, and open architecture ensure it can evolve alongside emerging technologies without losing effectiveness. In this sense, the B-21 represents more than a new aircraft. It signals a broader shift in how advanced aerospace platforms are conceived and sustained. By focusing on flexibility, life cycle efficiency, and future readiness, the B-21 Raider defines a new era of design, one where long-term relevance matters as much as immediate capability. The B-21 Raider is not just a new aircraft. It represents a fundamental shift in how the United States designs, builds, and sustains strategic air power. With the B-2 spirit, America pursued technological perfection at almost any cost, resulting in an extraordinary aircraft, but one that was rare, expensive, and difficult to scale. The B-21 reflects a very different industrial philosophy: capability at scale. Designed and produced by Northrop Grumman, the B-21 program prioritizes digital engineering, modular systems, and predictable production. This approach allows the U.S. Air Force to field a larger fleet, sustain it more efficiently, and continuously upgrade it without redesigning the aircraft from scratch. Instead of relying on a small number of irreplaceable bombers, the U.S. gains a resilient force that can absorb losses, adapt to new threats, and remain operational for decades. Industrially, the B-21 sets a new benchmark. It demonstrates how modern defense programs can avoid the cost overruns and delays that plagued Cold War-era projects. Strategically, it strengthens deterrence by removing uncertainty for adversaries. When a capability is both advanced and numerous, it becomes impossible to counter reliably. In essence, the B-21 signals a transition from elite, limited-run platforms to sustainable technological dominance, ensuring U.S. air power remains credible, flexible, and future-ready well into the mid-21st century. When viewed side by side, the B-21 Raider and the B-2 Spirit represent two different answers to two very different eras of strategic aviation. The B-2 was engineered to solve a Cold War problem, penetrating heavily defended airspace with unmatched stealth, regardless of cost or complexity. It succeeded brilliantly and remained relevant far longer than originally expected. The B-21, however, is not simply a replacement, it is a recalibration. It trades extreme specialization for adaptability, massive payloads for precision, and exclusivity for scalability. While the B-2 pushed the limits of what was technically possible in its time, the B-21 is designed to evolve continuously, integrating new systems, weapons, and software throughout its service life. In practical terms, this means greater operational flexibility, lower lifecycle costs, and the ability to deploy the aircraft in larger numbers across more locations. The B-2 proved that stealth could change warfare. The B-21 builds on that proof and turns it into a sustainable, long-term capability. Ultimately, the B-2 defined an era. The B-21 defines what comes next: an age where survivability, adaptability, and efficiency are just as important as raw performance. The transition from the B-2 Spirit to the B-21 Raider is not merely a routine modernization. It reflects a deeper shift in how long-term air power is planned, sustained, and evolved. This change matters because future security challenges are no longer defined by a single adversary, a single domain, or a fixed set of technologies. They are dynamic, distributed, and constantly evolving. The B-2 proved that technological surprise could redefine deterrence, but it also revealed the limitations of highly complex, low-quantity systems. The B-21 addresses those limitations by prioritizing adaptability, scalability, and sustainability from the very beginning. Rather than locking capability into a specific moment in time, it creates a platform designed to evolve alongside emerging threats and technologies. For the United States Air Force, this transition enables a more resilient force structure, one that can maintain relevance across decades without relying on costly redesigns or small, fragile fleets. For the broader defense ecosystem, it demonstrates how digital engineering, modular design, and disciplined production can deliver advanced capability without sacrificing affordability or reliability. Ultimately, this transition matters because it sets a precedent. It shows how future strategic systems can balance innovation with endurance, ensuring that technological advantage is not just achieved, but sustained.